Hi there, my name is Herman. In this video, I will briefly introduce our work on text-to-audio synthesis. This is a joint work with my colleagues at Adobe and my PhD advisors at UC San Diego. This work is done during my internship at Adobe, working with Xiaoyu. The goal of this work is to learn text-to-audio synthesis without using text-audio pairs. But first, what is text-to-audio synthesis? Basically, given some text query, we want to generate a sound that corresponds to the text. Here's a quick demo. So all the samples you just heard are generated by our proposed model. Now, text-to-audio synthesis is not a new topic. We've seen many papers on this topic since last year. However, all these existing models, as far as we know, all rely on large amount of text-audio training pairs. In this work, we want to take a different approach. We want to see if we can learn text-to-audio synthesis without using any text-audio pairs. But wait, why don't we want to use text-audio pairs? Here at the left, you see Lion5B, which is one of the largest open datasets for training language vision models. It contains 5 billion text-image pairs. Now, the largest text-audio dataset so far, the Lion Audio 630K dataset, contains only 0.6 million text-audio pairs. Also, it remains unclear whether we can scale up text-audio datasets to a size comparable to large text-image datasets. Now, if we look at all the YouTube videos, this is like 500 hours of video uploaded per minute. What if we can learn text-to-audio synthesis through videos? That's exactly what we want to explore in this paper. Long story short, we want to leverage the visual domain as a bridge to learn text-to-audio synthesis. We want to learn the desired audio-text correspondence by combining, first, the naturally occurring audio-visual correspondence in videos, second, the multimodal representation learned by pre-trained vision language models. And this offers two benefits. On one hand, we don't need any text-audio pairs. On the other hand, this framework can be scaled up to large video datasets. Now, before jumping into the details of our proposed method, I would like to introduce two important backbone models that we will use in our work. The first backbone model is CLIP, Contrastive Language Image Pretraining. In short, CLIP is a pair of image and text encoders that share a joint embedding space. This is achieved by contrastive learning. Here's an example. Say we have a cat image and the text cat, and a dog image and the text dog. In contrastive learning, we want to make close the embeddings for the cat image and the text cat, and similarly for the dog image and the text dog. In the meantime, we want to make further away all the other combinations. And this is how CLIP learns a bimodal representation for language and image. The second backbone model we use is the diffusion model. To put it simply, in the diffusion model, we take some ground truth image and add noise gradually in the so-called forward diffusion process. And our goal is to learn the inverse process, where we want to remove the noise step by step in the backward diffusion process. Once this diffusion model is trained, we can then put in some random noises, and the model will then remove the noises step by step and generate the samples. With that, let's move on to our proposed method. During training, we have access to only unlabeled videos. So we first train an image-to-audio synthesizer. Here we take the audio track of the video as the target to train our diffusion model, which works on male spectrograms. And this diffusion model is conditioned on one random video frame extracted from the input video. This video frame is encoded by the pre-trained clip image encoder, and the clip image embedding is passed to the diffusion model as the conditioning signal. Now, during inference time, the first approach we explore is to simply use a pre-trained clip text encoder directly. That is, we encode the input text query with the pre-trained clip text encoder and pass the clip text embedding to the diffusion model. However, this zero-shot modality transfer approach doesn't work well in practice. And this is because there's a significant difference between the clip text embedding we use during inference and the clip image embedding we use during training. So how can we overcome this modality gap? Thankfully, we are not alone, because this is a known issue in text-to-image generation. In the DALL-E 2 paper, they found that when we use the clip text embedding to train the text-to-image generator, it generally doesn't work well. So they proposed the diffusion prior model, which learns to map a clip text embedding to its corresponding clip image embedding. To zoom in a bit, in the ideal case, we'll assume that the clip embedding spaces for text and image are highly overlapping. However, in practice, that's not true. The goal of this diffusion prior model is to move the text distribution towards the image distribution in the clip embedding space. Now, with this diffusion prior model, we have an improved version of our proposed model. Instead of directly using the clip text embedding, we generate a fake clip image embedding as the condition for the diffusion model. And this significantly reduced the modality gap we observed previously. Also, this diffusion model is pre-trained on Lion 5B. In other words, we still don't need any text-audio pairs here. So here's a quick recap. During training, we train an image-to-audio synthesis model. During inference, we explore two variants. In the first model, we do a zero-shot transfer by using the clip text embedding directly. In the second model, we use a pre-trained diffusion prior model to convert a clip text embedding into a clip image embedding. Now, let's move on to the experiments. So in this work, we consider two data sets. One is the music data set, which contains high-quality music instrument playing videos. The other is the VGG sound data set, which contains noisy videos with diverse sound categories in the wild. And here are some implementation details, but I won't go into details. I just want to highlight one thing, that we use the big vegan model as the vocoder to convert male spectrograms back to waveforms. Now, here are some examples of the inference process. So this is the input noise. Let's listen to how this sounds. So this is basically the prior of the big vegan model, which sounds just like R2-D2 or robot noise to me. Now this is at 900 steps, which sounds more like a bass. And this is the final output at 1000 steps. Cool. And here we have more samples for text-to-audio synthesis. Also, recall that our proposed model has two variants. So here are some comparisons. So we also conduct a subjective listening test. We can see that the model with the pre-trained diffusion prior model significantly outperformed the baseline model. Now, during training, we are actually training an image to audio synthesizer, which is like a byproduct, but surprisingly, it works really well. Here are some demos. So here we can also compare the results with two recent papers on image to audio synthesis. Cool. In our listening test, this image to audio synthesis model also achieves state-of-the-art performance in its fidelity and relevance. In addition to the subjective listening test, we also compute some objective evaluation metrics to evaluate our models against other baseline models. Please check out our paper for more results. And with objective metrics, we can analyze the effects of classifier-free guidance used in the diffusion model. Here, we look at the FAD, which measures the quality and diversity of the samples. The lower the FAD, the better. So we can see that there's clearly a sweet spot when the guidance level W is 1.5. Also, from the CLAP score, which measures the adherence of the audio samples to the text queries, we can see that larger guidance level leads to stronger adherence to the text queries. And we could see the low CLAP score of the reconstructed ground truths, which shows how noisy VGG sound is. Finally, I want to talk about some limitations and future work. First, we noticed that many off-screen sounds occurred in videos, which poses a challenge in learning the desired audio-visual correspondence. Second, the system cannot handle purely audio-specific queries, such as loud, quiet, high pitch, low pitch, because they have little meaning in the visual domain. For future work, we are interested in enabling compositional prompts, such as piano and guitar. We also want to scale up the system to large video datasets. So, to conclude, we explore using the visual domain as a bridge to learn text-to-audio synthesis model from videos. And we propose a new text-to-audio synthesis model that doesn't need any text-audio pairs in training. Our proposed model achieved strong text-to-audio performance, and it also achieved state-of-the-art performance in image-to-audio synthesis. Please check out our paper demo in the links here. Thank you so much.